Okay, so in the last lecture, we have been discussed the power flow and dynamic stability consideration of interconnected transmission system. So in that, we have been just come to the conclusion that how the power flow through a transmission line, that is P, is the function of magnitude of one end voltage, magnitude of another end voltage, the transmission line reactance, and the angle of both the end voltage, that is E1 and E2, in a given two machine system. So here the power exchange among these two regions has been done through a transmission line, and how that transmission line reactance and that two end voltages magnitude and their angles make it to flow through it. Now, if we want to regulate this power exchange among these two regions by controlling the parameters of this transmission line, so that parameters are obviously as per this equation, that is E1, E2, X and delta. That E1 and E2 change. If suppose here in the graphical approach we describe that in detail, that if we control the line reactance X, then that is going to control the power angle characteristics of that given transmission line. So for a particular loading condition, let's say P0 and at an angle of delta 0 is the power flowing through this transmission line. So for that particular loading condition, if we change the X, then the operating point shifted from here to here, this point. Operating point shifted here. Means what happened? Same power we can transfer through a transmission line at a reduced load angle delta. That is, the stress on that line get reduced. Or for the same stress, that is for same load angle delta, we will able to transfer some more amount of power through it. Means we can say that more securely we can transfer the more amount of power through the same transmission line if it is provided with the line impedance compensation. So that is the one parameter which we can control. Second is if we able to control, this is the normal phasor diagram of phasor E1, E2. This is phasor E1. Phasor E2 was considered as reference. So according to that difference between these two, that is we call it as a voltage drop across the line, that is EL. And accordingly the current which is flowing through the line is I. Now for this given line, if one end of the line is provided with the shunt compensator such that the magnitude of this bus voltage, even if we increase little bit, magnitude of this E1, suppose we increase little bit. So because of this, what happened? The voltage drop across the transmission line, that is EL, which is equal to E1 minus E2, that phasor will change from this position to this position. Now this change in this phasor E1 minus E2, if we see, the magnitude of that phasor is approximately same. मतलब उनका जो length है E1 minus E2 का, that is approximately same. Only the phase angle which was get change of that E1 with respect to reference, this was the phase angle make earlier. Now the phase angle changed to this one. So the significant change in the phase angle of that voltage drop across the transmission line occurred because of changing the one end voltage of the line, magnitude of one end voltage. And because of this change in the phase angle, what happened? Whatever current was flowing through the line, that magnitude is also approximately same. इसका और इसका magnitude, only the phase angle shift of that current phasor through the transmission line has been changed. So यहाँ पे क्या हो रहा है? If we control the any end voltage of the line then it is significantly going to change the phase angle of current flowing through the line, and because of that it is contributing to the significant change in the reactive power flow through the transmission line. मतलब सिंपल है कि शंट कॉम्पेंसेटर अगर हमने लाइन को लगाया कहीं पे भी at the end, so it is help in controlling the reactive power flow through the line. Reactive power flow is not much effective because change in the magnitude of current is not that much, because of there is no much change in the voltage drop across the transmission line. Only the phase angle of that voltage it is changing significantly, and because of that the current phase angle changes significantly, and because of that the reactive power flow change significantly. Now this is what we talk about. One is X we talk, another E1 magnitude or E2 magnitude we talk. Third is rather than changing magnitude of E1 or magnitude of E2, if we change the magnitude of this E1 minus E2, that is, this is suppose your E1 minus E2, if we inject the voltage in series with the line such that it will be in phase with the voltage drop across the line. And because of change in this E1 minus E2 voltage, what happened? The magnitude of current flowing through the line, which was this one earlier, now changes significantly. मतलब यहाँ पे क्या हो रहा है, अगर हम लाइन के सीरीज में अगर हम वोल्टेज इंजेक्ट करते हैं and that injected voltage is in phase with the voltage drop across that transmission line, then that will significantly change the magnitude of current flowing through the transmission line. And because of that, there is a significant control in active power flow through this transmission. Obviously, if we want to control both active and reactive power flow through the transmission line, so that can be achieved by injecting the voltage, that can be achieved by injecting the voltage in any phase relationship with the your voltage drop across the transmission line. If we do that in 360-degree in any phase relationship with the voltage drop across the transmission line, if we inject the voltage, then according to that phase angle, there is a change in the magnitude of current as well as the phase angle of that current, and because of that there is a change in the flow of real power as well as reactive power exists. So as per this discussion, what we can say that X control is there, delta control is there, magnitude of E1 or magnitude of E2 we can control, or phasor E1 minus E2 we can control in order to control the real and reactive power flow through the transmission line. Now, as in the next part, what is relative importance of these controllable parameters? Relative importance of this controllable parameter. The controllable parameters are what? As I mentioned here, X is the controllable parameter, delta, that is phase angle, is the controllable parameter, magnitude of E1 or controllable parameter, or magnitude of, sorry, E1 minus E2 phasor is the controllable parameter. So how they are relatively important, that is what we discuss now. So here the summary for that relative importance has been mentioned. How by controlling the line reactance, whatever discussion we did now, how by controlling the line reactance here, we can control the current flowing through the line. And obviously, by controlling this current flowing through the line, by controlling X, we were able to control the active power flow through the line. We will be able to control the active power flow through the line. Similarly, by controlling the phase angle by means of phase angle regulator, it is possible for us to control the flow of active power through the transmission line. Similarly, we talk about injecting the voltage in series with the transmission line, how it is contributing for both active and reactive power flow through the transmission line according to its phase angle of that injected voltage. Later, there is one point discussion is there that the rating of that series compensating device. Let's consider that we have a transmission line, and this transmission line is provided with some Earlier your voltage drop is suppose EL as what we say E1 minus, this is E1 minus E2. Now this is EL is equal to E1 minus E2. Now in order to control the voltage across this transmission line, we add up one capacitor, variable capacitor we can say, in series with the transmission line. So what will be the rating of this compensator? What will be the rating of this compensator? Obviously, when we add the capacitor in series with the transmission line, it will carry the rated line current. That capacitor also has to carry the rated line current of that transmission line. Whereas, how much voltage we want to compensate, according to that, its rating for injecting the voltage has been decided. And this V into I is nothing but the rating of your compensator. Whatever compensator you are utilizing, its rating is V into I. V is the injected voltage by that compensator and I is the rated current of. For a given transmission line, its power rating is what? E into I. Line into I is the rated current of the line, is the power rating of the line. Obviously, if we consider the example of 400 kV transmission line, 400 kV transmission line. Now we know for 400 kV transmission line or any transmission line, the acceptable permissible variation in the voltage is plus minus 10%. Means what? Let's consider that this transmission line is designed for a 400 kV and its acceptable permissible limit for variation is plus minus 10% of that 400 kV. So, if sending end is energized by 400 kV, so the receiving end voltage will be either less of 10, less by 10% to that 400, that is 360 kV, or maybe greater than that 10% to the 400, that is 440 kV. Means what? The voltage drop which is happening across the transmission line, that EL which is happening across the transmission line, have a maximum value of 10% of the rated voltage. That is, we can say 40 kV. Please try to understand. Now 10% of that rated voltage is the maximum voltage drop which is permissible to accept in that transmission line while designing it. So out of that 40 kV voltage drop, how much percentage of that we want to make it controllable? जैसे अभी हमने यहाँ पे बात किया कि this is what the voltage drop happening across the transmission line. This is what the voltage drop happening across the transmission line. Now some 25% means we should be able to control this either 25% of its total voltage drop. मतलब क्या 25% लेस भी हम कर सकते हैं और 25% उसमें ऐड भी कर सकते हैं. So that is what the compensator voltage rating in order to compensate that transmission line by mean of injecting the voltage in series with the transmission. So ये अगर मैं 25% बात करता हूँ, 25% of the EL. So here 40 kV is the EL for 400 kV transmission line. So this V, what I am talking about is the 25% of this. 25% of this means what? V should be 10 kV, maximum rating of the voltage which is we are going to inject by mean of this series capacitor compensation is 10 kV for 400 kV transmission line. So the VR 10 kV, that is 10 into e to the power 3, that is 10 kV into whatever will be the I, that is what the rating of your compensator. Whereas the rating of the line is what? 400 kV e to the power 3 into I. So if we talk about the rating of this compensator in terms of the overall rating of the system, in terms of overall rating of the system, so how much it will be? So this I will be get cancelled, 10 to the power 3 will be get cancelled. So this is 10 ones of 1, 10 fourths of 40. So 1 divided by 40. So 1 divided by 40 means how much it is? 1 divided by 40 means in terms of percentage if we talk about, so it is 2.5%. It is around 2.5%. Means what? The MVA rating of series compensator which we are going to use on the transmission line in order to provide the 25% compensation to cross it, then the rating of that compensatory will be only 2.5% of the overall rating of that transmission line. 2.5% of overall rating of that transmission line. So that's why it has been mentioned here that if we see the MVA rating of the series controller, which will be often very small fraction of the overall throughout MVA rating of the transmission. And with example, I will just dictate you that how that rating will be 2.5% of the MVA rating if you are going to provide 25% compensation for the voltage drop happening across the transmission. So this is what about the relative importance of this controllable parameter, how X is controlled current and then controlling the reactive power and real power, how delta control is there, how magnitude of E1 or magnitude of E2, how E1 minus E2, that is EL, or the combination of these all in order to control the real and reactive power flow through the transmission. Now the next point that we are going to see is the basic types of FACTS control. Now here in your curriculum, if you see, it is basic types of FACTS control. Sorry. Basic types of FACTS control. Just a minute. Basic types of FACTS control. Now, there are many more particular FACTS controllers according to their, we can say, topology or their, we can say, configuration or use of and devices unit action. But fundamentally, according to its connection to the transmission line, according to that FACTS controller connection to the transmission line, it is having an 4 basic types of FACTS control. And that is based on, as I said, how it is connected to the transmission line. If the FACTS controller is connected in series with the transmission line, then it is called as series control. If the FACTS controller is connected in shunt with the transmission line, then it is called as shunt FACTS controller. Please try to understand what I am saying here. If suppose this is the transmission line, if I am connecting a FACTS controller, some FACTS controller in series with the transmission line, then it is called as series controller. If I am connecting that FACTS controller in shunt with the transmission line, here is suppose some FACTS controller that I am connecting in shunt with, means in parallel with the bus bar with respect to ground. In parallel with the bus bar to the transmission, then this is called as a shunt control. There is a possibility of this bus bar is connected to more transmission line. These bus bars are having some additional transmission line, and that transmission line is also provided with this series FACTS controller. And these two series FACTS controller, which are provided on that individual transmission lines, which are connected to the common bus either at this one end or both the end. So according to this, what happens, the power which is going to get controlled through this transmission line, automatically going to control the power flow through this transmission line. So there should be a coordination between these two FACTS controller which is there on that individual transmission lines. So such combination is called as series controller. Means if more than 2 series controllers are used on your power system in order to regulate the power flow through the individual transmission lines, then that can be, we call it as a series FACTS controller. Series shunt means what? If the transmission line is provided with the series as well as shunt fast controller. जैसे कि ये line में series में भी दिया है हमने और bus bar को shunt में भी दिया है. So this is called as a series shunt controller. As I mentioned that these basic types of fast controllers are classified only based on their interconnection with the given transmission line. How it is connected to the transmission line, on the basis of that, this classification has been framed. Now we need to see what are doing basically, or how in principle they are playing with the parameters of that transmission line. Now, as I mentioned, here the symbolic representation for the fast controller is shown by this figure A. Means what? One box in which a self turn off capability fast devices, self turn off capability power semiconductor devices here. So this is, you can see, a power semiconductor device having a gate terminal which is used to control the turning on and off of this device. Obviously, it is only used to control the turn on, because the device which is used for controlling the turn off has been represented by, let's say, this is the symbol for diode. If it is provided with this gate terminal, then it is SCR. And if this gate terminal is given by the cross symbolic presentation, then it is called as the self turn off capability power semiconductor device. Self turn off capability power semiconductor device. That is, we can call it as a IGBT. Like, I think such symbol is used somewhere in the definitions. Yeah, here it is not there. Okay, anyway. So like IGBT, that IGBT is having a self turn off capability. So that's why that representation is done by this symbol. Now this is the symbol for your SCR. So fast controller symbolically represented controlled power semiconductor device in a box. Controlled power semiconductor device in a box. That is the fast controller. And now when this fast controller is connected in series with the line, you can see this fast controller here is connected in series with the transmission line. Then it is called as a series controller. Then it is called as a series controller. Now, what is this series controller is? What is this series controller is? This series controller is either a variable impedance, that can be either a capacitor or a reactor, or a voltage source, of fundamental frequency or subsynchronous frequency or a harmonic frequency or a combination of that. Please try to understand what I am saying here. This series controller can be a simple variable impedance. It can be a simple variable impedance. Or that simple variable impedance may be a capacitive reactor or maybe an inductive reactor. Or it can be a voltage source. It can be a voltage source of your rated fundamental frequency of your overall system, or it may have some harmonic component in that voltage source, or may have some subsynchronous component. Please don't get confused with the harmonic and subsynchronous. Harmonic is an integer multiple of your fundamental frequency. Harmonic frequency means when suppose your fundamental frequency is 50 Hz. So it is a multiple of that fundamental frequency by the integer number, like 2 times, 3 times, 4 times. Like that is 100, 150, 200, 250. So that is, we can call it as a multiple of your fundamental frequency integer number is called as the order of that harmonic. That is, we call second order, third order, fourth order. That is, by that time it is of fundamental frequency, that component is there. Whereas subsynchronous means less than the fundamental frequency. If that component unwanted rather than fundamental component which is there present in the source voltage, if it is less than of fundamental frequency, that is, it may be 2 hertz component, maybe 5 hertz, 10 hertz, 15 hertz, 20 hertz, 14 hertz, 50, 25 hertz, 30, maybe up to 49 hertz. So it is less than of fundamental frequency component is there in that, then it is called as a subsynchronous component. So here, as I mentioned, this series controller is nothing but can be a variable impedance like capacitor or reactor, or a voltage source of fundamental frequency, or a subsynchronous frequency, or a harmonic frequency, or the combination of that. Combination of that means it is having some fundamental along with some subsynchronous component as well as the harmonic component presented. In principle, what this series FATS controller is this? In principle, this series FATS controller inject voltage E in series with the transmission line. Please try to understand. As this series FATS controller is connected in series with the line, so in principle, that series FATS controller inject voltage in series with the line. And as long as this injected voltage by this series FATS controller is in quadrature with this line current, then this controller exchange only the reactive power with the line. Because as I said, if this E is in quadrature with I, let's say suppose this is the phasor of I, and in quadrature with this, means either 90 degree leading with this I or lagging with this I, we are injecting the voltage by means of this compensator. So what happened? It is act like that this compensator is injecting reactive power, exchanging reactive power with the line. Obviously, whether it is absorbing or injecting, that is decided by whether this E is led by I 90 degree, then in that case what happened? If this injected E is led by 90 degree with the I, then we come to know that I is lagging with the E. So it is act like this compensator is acting as some additional reactor is connected in series with the transmission line. Means it is like that it is absorbing a reactive power from the transmission line. Absorbing reactive power from the transmission line. If this E is 90 degree lagging with this current, what happened? It means that your current I is leading with the E by 90 degree. It is like that some capacitor is connected in series with the transmission line. And it is mean that it is injecting reactive power into the transmission line. Means that FATS controller is now injecting the reactive power into the transmission line. But where it is? As long as that injected E is in quadrature with the I. So if we use a voltage source as a compensator and by means of that we inject this voltage E with the line current I such that it is in quadrature with this I, it exchanges only the reactive power. Now, whether it is absorbing or generating, that is how this E phasor we are making with the I, that is decided. And that is look like a capacitor connected in series with the line or reactor connected in series with the line. So either you go with the capacitor connected in series with the line, it is like a equivalent to some voltage source is connected and that injected voltage by 8 is 90 degree lagging with the current flowing through that line. If you connect the inductor in series with that line, it is as source connected in series with the line such that that injected voltage by 8 is 90 degree leading with the current flowing through the line. That's all. So in principle, we have to just keep in mind that fast controller, series fast controller inject voltage in series with the line. And accordingly, how this voltage makes phase angle with this line current, according to that, it exchanges the real and reactive power with the transmission line. This whether it is injecting reactive power and absorbing real power or any combination, that is decided by how this E we are injecting with reference to the line current. So this is what about the series fast controller. Second one is the shunt fast controller. Now, similar to series fast controller, this shunt fast controller can be impedance, that is variable impedance, like capacitor or reactor, or it can be a voltage source of fundamental or subsynchronous or harmonic frequency or the combination of it. And in principle, this shunt fast controller inject current in the transmission line. In principle, this shunt fast controller inject current into the transmission line. And as long as this injected current by this shunt controller is in quadrature with the line voltage, as long as this injected current by this shunt compensator is in quadrature with this line voltage, that is system voltage, it exchanges only the reactive power with the supply system. Obviously, how this current, now here in this case, E is the reference and accordingly I you are regulating. So here in this case, the same plot will be there. Only here, rather than this, you can talk about this E as a reference, that is line voltage of your transmission line as a reference, and with reference to that, how current you are injecting by, okay. So with reference to this line voltage E, how you are injecting the current, either 90-degree leading with that E or lagging with that E, you are injecting into the line, and that will decide whether it is acting like a source of reactive power or sink of reactive power, or it is behave like a capacitor connected in shunt with the line, or reactor connected in shunt with the line, and so on. So this is how the shunt compensator and series compensator is there. So in our mind, we need to keep that series compensator inject voltage in series with the line, and how it is in phase relation with the line current. Accordingly, it exchanges real and reactive power. Shunt compensator exchange current with the line, and how it is in phase with the line voltage. Accordingly, it exchanges the real and reactive power with the line. So this is what about the series fast controller and shunt fast controller. Series controller. As I was giving you the example that suppose there are two AC transmission lines are connected in parallel to this one particular bus bar, and these both are provided with their individual series fast controller. Means what? This series fast controller is injecting voltage V1, and how it is in phase relationship with the current which is flowing through that line. According to that, it decides how this fast controller is injecting or absorbing real and reactive power with the line. Same is the case, this fast controller will inject voltage V2 in series with the second transmission line, and how it is making a phase relationship with the current flowing through that second line, that is I2. According to that, it exchanges the real and reactive power with the transmission. Now, when this series controllers are operated in a coordinated manner. Now, why we need to operate them in coordination? Because here if you see, it is a single bus, two is that both the transmission lines are connected. So any flow control happen through a one transmission line, that is automatically going to alter the flow of another transmission line. So while controlling the flow through a one particular transmission line, the care or the coordination has to be made with the another transmission line, such that your no line will be get beyond the load condition, and that whatever power you want to take it out or take into this bus bar has to be get fulfilled. So either these buses we are operated independently in a coordinated manner. So one coordinated control we can say like this, which will generate the firing pulses to their power-based FATS controller devices, and accordingly they will inject the voltage in series with the line in order to fulfill your requirement. But if these FATS controller are connected commonly by a DC link, if this FATS controller is connected by commonly by a DC link, then it is called as unified controller of that series FATS controller. So this is we can operate either in a coordinated manner or a unified manner. Unified manner means what? As here the common DC link is provided. So whatever exchange of real and reactive power this one converter will do with this line 1, according to that it will either inject the real power or absorb the real power. But if it is injecting the real power, so from where it has to take out? From where that real power it will get? Or if it is absorbing the real power from the line, so where it has to deliver that real power? So that is did with the common DC link. So through this common DC link, the real power exchange between these two converters has to be done. Means if one converter is absorbing real power from that transmission line, then another converter has to take that real power. Another converter has to take that real power from this common DC link and inject into the another transmission. So here, if this series controller is provided with a common DC link, then it is called as the unified series controller, and it is also named as IPFC. It is also named as IPFC. That is interline power flow control. That is interline power flow control. Means the power flow among these two transmission line, the power flow among the two transmission line, that is we can call it as the interline power flow control. So that can be done using this series controller if they are having a common DC link. If they don't have a common DC link and having a coordination control, then it is simple called as a series control. Obviously, in principle, this series controller and this series controller act like a series controller. Means they inject the voltage in series with the line, and how that injected voltage is there with respect to the current flowing through that line, accordingly that power flow through that line, that is real or reactive power exchange by that controller to that line has been decided. Similarly, the fourth one, as I said, series shunt controller. So here the example is that one series controller which is injecting voltage in series with the line, one shunt controller which is injecting current into the line, and these both series and shunt controller are controlled in a coordinated manner or provided with a common DC link like this figure, provided with a common DC link. If it is so, then it is called as UPFC. It is called as UPFC, that is unified control. So that UPFC stands for unified power flow control. Unified power flow control. Obviously, in this case, this E injected according to the current flowing through the line, what phase relationship it is having, that is going to decide how much real and reactive power it is exchanging with the line. Whereas how this I is injected by this shunt controller with respect to the voltage of this bus bar or the point of connection, accordingly that I relationship with this E, it exchanges the real and reactive power to the transmission. But obviously, real power is the unidirectional flow is there. Means either this converter will take the real power from the line and feed it to the common DC link, and then this converter will take it from that common DC link and inject into the transmission. So according to your need of operation to that controller, according to your need of operation of that particular fetch controllers provided in your system, that requirement point of view, you can operate them in a either coordinated manner or in a unified manner. If it is operated in a unified manner, then it is called as Unified Power Flow Controller, that is UP. Obviously, this combination is possible not only with the two fetch controller. Like if the bus bar is having a multiple transmission line, those who are provided with the series fetch controllers, and this bus bar is provided with the shunt fetch controller, and that all fetch controller DC side is commonly connected by a common DC bus bar, that is called as common DC. Then this is, we can call it as a example of extended series shunt controller. So rather than there is a single series controller, there are some two series controllers provided on the transmission line which are connected to that particular bus bar. So this is an example of series shunt controller. So hope you understand. Hello, now am I audible?
Yes, sir.
Yeah. So based on the interconnection of this patch controller with the transmission line, they are classified. Now, in the coming lecture, we will see the relative importance of these types of patch controller, how they are relatively important to each other. Means what is the we can say identity of series controller, what is the identity of shunt controller, where more effective for what applications and that all. So that relative importance of these types of controller we will discuss in the coming lecture. Okay. So here hope you understand what series controller is does, and in principle it inject voltage in series with the line, and how that injected voltage is there in phase relationship with the current flowing through the line. Accordingly, the real and reactive power exchange by it get decided. So these all thing I has been discussed here. Hope you will go through it again and try to understand it more clearly. Okay. Now we can stop here only. You all please mark your attendance. Please mark your attendance. Those who will mark can leave the meet. No problem. Please mark your attendance, and after marking of attendance, you can leave the meet.